we considered a fluid element, right? And then we applied pressure on different sides and used Taylor series, and I kind of stopped the lecture for a few minutes and tried to explain you what Taylor series basically does, right? That is important, because mathematical version you already know how to perform Taylor series expansion, but physically what does that mean in terms of the gradients. And the last relation which we kind of derived was what? Which was this was true for fluid at rest. For fluid at rest. And what does this gradient of P means? Right, it's a change of pressure. One thing you should be very clear, you should not ever say rate of change, because rate is generally, by convention, it is related with respect to time. So there is something known as temporal change, let me put it that word. And it has something to do with time. And there is something known as a spatial change, which has something to do with the space, right? And what is space is X, Y, and Z. Clear? Okay, hurry up, settle down. Is that door open? By the way, anybody coming late, please use that door, right? Otherwise we have like 40, 45, 50 minutes of class, and we are settling in another 10 minutes just to avoid disturbance in the class. Anyways, del P, mathematically that means partial P, partial X, right? Anything else? I think it's on. The fan is, I think, running at full RPM. Is going to check it anyways. Now it's clear, I guess. Too much. Wow. I feel like a singer or something. A vocalist maybe. Okay, anyways. Partial P, partial X. What should I write in front of it? 0 to this. Right? And then I also have, I'm just expanding the equation. So let's put this here. And we have a gamma K. So far so good. So what I'm going to equate is, since these are vector quantities, everything with respect to I is a separate equation. Everything in the direction of J is another equation, and K as well. So if I write in terms of the I direction, partial P, partial X, is there anything? Okay. For the J, I have partial P, partial Y. And for the kth direction, I have partial P, Z, and minus plus. Should I put equal sign? Right, so these are kind of, you can say, the governing equations. That's how the fluid at rest would feel the pressure variation. So very interestingly, if you look at this, that means if you have a vessel, right? So if my axis is somewhat like this, okay, just for for consistency, let's say something like this. It's a 3D vessel now. So you have water everywhere. It's a small pot kind of thing, rectangular pot. So the pressure does not vary in X direction. Let's say if you are in a swimming pool and you're swimming at a depth of like 6 feet, right? If you remain at the same level and move right and left, you should not see any variation in the pressure as long as it is static, right? It's not river that there is some stream coming. If you are in a static pool swimming at a point and you are going in X direction, Y direction, coming up is a Z direction, right? Coming up is a Z direction. So other than the Z direction, if you are swimming at 6 feet underwater, you should not feel any variation in pressure. So if you have a gauge and you are swimming, you should not see any variation as long as you are moving in that plane, in that XY. So again, if you are moving in the Y direction, you should not feel any difference. This is also clear. But the moment you start to come up, or if you start to go down, ascend or descend, then that pressure gauge will tell you that now there is some pressure which is changing. Clear? So that should be a physical concept of pressure variation. It only changes when the head or the water level above you is either increasing or it is decreasing, because that is what is causing pressure variation, right? If you just move right and left at, let's say, 6 feet, the water which is above you is the same, so the amount of pressure being exerted on you is absolutely the same. So okay, partial P, partial Z. Okay, now if you are moving in this direction, it has something to do with the specific weight. Everybody knows what is gamma? What is it? Rho G. Clear? So now if you are moving right and left, no variation, but the moment you come up and down, that makes a difference. Now let's say if you are swimming in water, and let's say if you are swimming in honey, you are dreaming and somebody put you in a pool of honey and you are kind of at 6 feet under that honey jar, a huge honey jar, you would maybe collapse because the amount of density associated is, let's say if you are in mercury, you would die anyways because of mercury. But let's say if you happen to survive with some scuba diving equipment, you will still feel that the amount of pressure on you is huge because of the density of the fluid in which you are swimming, you are immersed in. So that is important thing. Okay, so having said that, let's go now to, this is something which I finished at the last moment, so I just wanted to make sure that you understand the physical concept of this partial P, partial X, partial P, partial Y and Z. Okay, so next thing which we have is incompressible fluids. So in exam, if you see something which is the gradient of pressure, you should be able to answer that. If I say maybe pressure is scalar, vector, so you should know what is it. It's a vector, right? I still see some heads nodding. Yeah, of course. It's a scalar quantity, right? So next thing we are going to study is this, which is, okay, now coming from the previous equation, I remember, I think I also went over this one, but is this. First thing first, why did I change this partial P to dP dz? Because of this. For this particular problem, pressure is only a function of Z. What is the technical term of this XYZ? What kind of variable is this? Independent or dependent? Oh, I see a split in the class. Should I go for a vote or what? Okay. If the instructor is there, it's dictatorship, right? So this is an independent variable. If there is only one, we can replace this partial by a complete derivative. That is why dB dz is minus gamma. So now all those who hate mathematics, it's a bad news, because I'm going to do integration. dB minus gamma dz. Anybody having any issue with this? What should be the next step? Good. Integrate. Let's say definite or indefinite? Now clear? I have put certain conditions on it. If you are kind of swimming in a pool, then you say that I went from this depth to another depth, Z1, Z2 kind of thing. So that's what it is. And what should it be? Okay. Minus gamma. Okay. Everybody understand this step? Straightforward, not tough. I'll finish the class like 5 minutes early. I need to talk to you guys regarding the quiz which we had last time. Non-technical stuff. Right? So don't worry, I'm not going to distribute it some zeros or ones, but something else. Okay, so let's say Z1, they are the vertical elevation. Everybody understands why it is a vertical elevation. I in the Z direction. So if I write this as P1 minus P2 is like gamma of H, so where H is right, and in other words it's P1 equals gamma H plus P2. So there's something which I started with, incompressible fluids. Incompressible fluids. So I also said it's gamma of G. How many times would you observe G changing? Most of the time, if you are dealing with some engineering based problem, G fairly remains constant. The amount of variation in G, if you are swimming at 6 feet and you go till 10 feet, it's almost negligible. It's almost negligible. So as an engineer, you kind of say that G kind of fairly most of the time remains constant. The thing which changes is density of that fluid. So if this density does not change, that is known as what kind of fluid? Right. Compressible? Who said? Incompressible. And we will also see the effect of compressibility later on. But as far as this thing is concerned, it is incompressible fluid. Clear? Now, what kind of equation is this? Linear, non-linear? Oh, there is a time gamma times H, so it should be non-linear, right? Okay. And it's a linear change, linear variation. So the change in pressure between 2 points is linear. That would mean that if these are 2 points and let's say the pressure is P1, and let's say we'll call this P2 and we have pressure P1. What is a linear change? What does that mean? If that's the same, if the pressure is some quantity here, so the pressure increases by the time it is here. So far so good? Okay. And we also call this as question. H as the pressure head. Clear? H is just known as the pressure head. That how much pressure variation is on top with respect to the first point. Straightforward thing. Okay, now there is a figure in the book. Let me kind of draw it, and this will give you some idea what. Something like this. Okay. Let's say we have different vessels here, and due to some reason we have fluid in here. Let's change the color a little bit. So pressure at all these dots, that is same, that remains same. Irrespective of the kind of pressure heads which you might have at different vessels, but at a certain depth, right, the pressure variation remains same. Okay, if I ask you something using this kind of principle, there is something known as the Pascal law, like an FSE kind of stuff. How many of you know this? I think we also covered it in the class, did we? So if I use it in order to, and this is the property of incompressible fluid, that's why I'm talking this. It can help you. How can it help? How can it help? Right. Hydraulic press is a good example. Anything else? Right, something like this. So if I draw something which is this one is and this is the piston here. Think of them as a straight line, by the way. F1 is P times A1, F2 is P times A2, and it is all fluid in. So it's more or less the pressure transmission from one point to the other. And I wrote P both sides, so it means the pressure is the same. How would it differ if I have a compressible fluid rather than incompressible? Let's say we have water in this hydraulic press, or any other oil in this hydraulic press. What if I put air in it? What would happen? Right, so the transmission of pressure won't be the same. because what it will do is it would bring the molecules of air closer to each other. Compressibility effect. And we did some example where in order to press or compress 1% volume of water, we required like 3120 psi, something of over 3000 psi. And the pressure which we experience right now is 14.7, 1 atmosphere. So you can well imagine how many times the pressure should be increased in order to compress. Question. In order to compress water, right? Okay, next thing is, by the way, I also mentioned, let me give that number as well for air. We have already discussed something known as Mach number. If it is less than 0.3, it is generally treated as incompressible. Incompressible, especially since we have already studied Mach number, that's why I thought it's kind of important. Beyond it, what happens is the compressibility effects, they start to come in your problem. Then you have to consider the amount of compressibility which is taking place. Good? Okay, let's do a quick example. This one is interesting because of okay, so the statement, it says something that some other water has seeped in a fuel tank. So you have one layer of water, and then on top of it you have a gasoline. You have gasoline. So what it asked is that if the specific gravity is 0.68, what does that mean? What is specific gravity? Is density or gamma? It doesn't matter, right? Because of G effect, it's just a multiplication by G, and I'm sure G does not vary between the side. So it with respect to H2O, something like this. Okay, now we have question. You have this height. I'll not crunch the numbers. That's not my area of interest. And you have this height. So the pressure distribution is given as, we have this formula. Somebody has a book, I guess. So we have this height as H1, H2. So this gamma is for that gasoline. We are coming from this height, we are coming till this. If the pressure is P naught here, the pressure should be higher or small here? Higher or smaller? Right, so let's write higher. I'm trying to solve it through intuition, not by number crunching. So you have some pressure P naught plus gamma H. Gamma of what? What kind of liquid is this? Gasoline, right? So we have to put in, this one is H2O or gasoline, right? And height as H1 or H2. Okay. Because if I start putting numbers, then people will get confused with the units. Oh, we have been working in meters. We wrote 17 feet, right? So whatever the units are, I want you guys to understand that as you come down from this height to this one, the pressure should increase. That's the number one thing you should kind of realize. It's interesting, few people, their eyes are closed, but they're still nodding at my question. Yeah, you're right. At least they are present and they're listening. If they're not watching. Okay, so the next thing is you compute this P1. And now the next thing is P2. How would you compute it? Any wild guess? Gamma H plus P1. And what is gamma here and what is H? And gamma of? Okay, good. So now if I cook up a similar kind of question and I come with a quiz next time, just to wake people up, if I come up with a quiz next time, so everybody should be able to solve in like 5 minutes, like peanuts. Easy, right? No big concepts involved, but the thing we should be very much clear. If anybody does something that the pressure at the top is like let's say 20 psi, and as you come down it is now 10, so I'll deduct -5 even from quiz number 1, not 0, -5 from the previous quiz as well, if you have already not gotten a 0. Otherwise I have to keep a track of negatives. Anyways, this is important. People studying this fluid at rest, sometimes they are just confused of some number crunching. They kind of memorize a formula, and without thinking what is happening physically, they just come up with some numbers which are not real. So you kind of violate a physical problem and come up with some winning numbers which are not correct. Okay, next thing, we have compressible fluid. What is the governing equation here? Anybody this rings a bell? No? Yeah, why are you afraid? P equals rho RT. So that governs the variation of density, because compressibility, what is it doing basically? Let's say if you have bunch of molecules, and the next step, what you do is you bring it here. So those molecules, they are now close enough. What should change? Right, as per unit volume. There is something which I have not said. The kind of process. What are those things? Now, what kind of processes? It could be, right, isentropic, isothermal. So that is something which you need to be careful with, that under what circumstances you have moved this piston. What kind of environment did you keep? Did you change did you allow us to vary the temperature? Because P equals rho RT, if these things are changing, temperature may also vary. Or is it isentropic? Like no heat transfer, and it's like frictionless. So the terms which you should know, and this is something I think already mentioned in the class and already mentioned in some other course as well. isentropic, right? And we have dP as variation in this is G PRT. How did I do this? Wild guess. All those who are sleeping, if it comes in the quiz, tough luck. It's nothing but substitution. Nothing but substitution. So it's what is here is and is here, separation of variables. And we have, let's say it varies from P1 till P2, constants, Z1, Z2, some crazy mathematics, but what you should get is P2 is P1 exponent of minus G, Z2 minus Z1. Okay. Some isothermal conditions maybe. Temperature does not vary, so it is T0. Now, critical point. Let me ask you this. Last time, which we once we said that the pressure varied linearly. If it is an incompressible fluid, you go from this point to that point, the pressure will change linearly. Everybody is clear? Changing linearly, what does that mean? It was gamma time h. It was that simple. Right? But now the pressure is varying exponentially. That means there would be kind of an exponential curve which would define the way pressure varies between 2 points, P1, P2. Knowing P1, if you want to find P2 at this height, this is what will be there. Z2 minus Z1 is kind of an edge, and then there is an exponential function. Negative defines that it is not going to increase, it is going to increase this way. So far so good? No? I think we need a quiz or something. Okay, last, do I have slides or what? No. Still have time. We want to keep it, and I need some extra slides. Step. This is just a general information about the standard atmosphere. I don't know if I gave an example in this class or the other one. I also mentioned aircraft flying at some altitude, let's say 36,000 feet. Right? I don't know. Did I give this example here? Yes? No? Are you in both sections or what? No. Anyways, generally aircraft flies at 36,000 feet. It's an optimum kind of altitude to save fuel. Let's not go into details why this is that way, but the variation of pressure densities in atmosphere is very strange. It's strange. And if I have to draw this, then it would be clear, let's say. If this is kind of temperature here, and we have altitude on y-axis, altitude. So we are living somewhere in, let's say, 25 degrees centigrade at sea level. Let's say we are living at Karachi. So temperature is, let's say, this. So at an altitude of about 11 kilometers. No, that's the tough part here. minus 55. This is kind of, let's say, 0. I have to draw a straight line here. Yeah. And this temperature is like 55, minus 55. So by the time you are up there at 11 kilometers, the temperature drops to this, approximately 56, 55 negative. And then after a while, this is 11 kilometers, which is about like 36,000 feet maybe, approximately that. Then it stays constant. And this remains till 20 kilometers, approximately 20 kilometers. And then about 32.2, this varies and becomes like a minus 44. There's a good picture in the book, by the way, so, and decent numbers as well. And then by the time it is like 47 kilometers, this thing is somewhere here. Again, it changes linearly up till at minus 2.5 centigrade. This is something like here. So it's a very strange variation, and the pressure over here at this point is like 0.1 kilopascal, and here is 0.9 kilopascal, and the standard atmosphere is 101.3 kilopascal, something like this. So you can see the kind of variation which is in the atmosphere. And this is a very interesting phenomena, and whenever there is a vehicle design, flying vehicle design stuff, you have to consider all these variations, whether it is an aircraft design or a missile design. So you have to be very careful that it should be able to resist all this pressure variation and the temperature variation in the atmosphere, right? And some of the regions, they are known as where am I? Okay, I am here. Troposphere, and this is stratosphere. And I don't know which one is like a mesos and stuff, something like this. So every region is given us this is not, I'm not sure this is the one, but then it goes straight up. So a lot of pressure variation. Okay, and then if I have, these are linear relations. And if I write something like this, z is the change in altitude, change in altitudes. What is beta? Is the slope of these things, how things are changing. Right? Since this was a section in the book, I thought, and then it's an interesting one. But next time we meet, we'll do this, the way the pressure is measured, maybe a couple of examples. And this is a little bit important because next time, by next year, as you go in your junior year, you will be doing certain experiments. You will be doing certain experiments from the viewpoint that a fluid is passing through a tube with different, let me draw it, it's interesting. So you should keep it in your mind, and maybe after 1 year, so something like this. right? So it's coming like this. So these are manometers. The water is here. So due to this effect, which is sometimes known as a Venturi effect, water would tend to go fast or slow. Okay, so let's say fast, and here we write slow. If it is moving slow, the pressure should be high or low. Okay, so this height should be kind of different, and here the height should be different of water column. So measurement of pressures. So this is an experiment. I think I have seen this equipment in our lab as well, but this is a typical experiment where you kind of measure the pressure. And this used to be old times, but if there is a new lab, things are digitized now, so you can see pressure variation digitally. Things are kind of computerized, but the point is that it used to be like that, right? And it's still good. In order, if you are measuring pressure with respect to the height of water level in manometers, you can apply this P2 minus P1 thingy and compute the pressure. And once you know the pressure, you can compute the velocities as well. Good. So next time we meet, we'll cover a couple of more topics, and then I think it's more or less now pressure variation and fluid at rest. So you will solve more problems on these, which would give you an idea that, let's say this is important from the viewpoint of dam construction. You have different water levels, and there is a wall you have created, so how pressure would vary and how much would the pressure if they open the gates, right? So what would happen? Because the water in dams, we say that is static. There is some application there as well, but there are tons of problems in the book, and I expect you guys to practice all of them. I can choose any one and ask a question in the exam. Feels good? Bad? Concepts. Emphasize on the concept. That is important. Okay, so that's all. The one thing which I have to do is roll call, attendance. So let's do that. Let's go. Please close guard them. We are done.